Okay, and we're off. Hello and welcome everyone to what is hopefully going to be an exciting and entertaining video tutorial on how to perform a motion simulation. And hopefully the last one I have to record, because it's probably the 5th or 6th time I'm doing this and it's getting really late, I'm very tired, I'm starting to lose my voice, and if I have to record this one more time, I'm going to quit my degree and pursue another career. So with that out of the way, let's get started. So I'm just going to bring up the assembly model here. So as you probably read from the title, we're going to be working on a full bar linkage. So it's really quite a simple model. And before I go any further, I should mention that if you don't know how to make this in CAD in general, then you really shouldn't be doing or performing motion simulations. You do need a baseline knowledge of CAD. Of course, it's not necessary, but I mean, with anything, you really do need some previous or prior knowledge of the subject to actually perform some of the harder tasks. So yeah, I highly recommend just at least knowing how to do this. This is really a simple model, so if you don't know how to do this, then please just stay away from motion simulations, please, on my request. So let's get started. So right now we're in the modeling environment, and we're just gonna go to the motion environment. So you just go to application, simulation, group, and motion there. And so okay, so now as you can see, we're in the motion environment, but whereas before that was modeling. And so I'm just going to quickly talk about the UI, or the user interface, for those of us who speak the Queen's English. Yes, so at the top we have sort of, well, the home tab, and this is pretty much what we're going to be, these are where all the options are for you to perform the motion simulation. So everything you will need to perform a motion simulation is going to be here. And on the left here, the motion navigator, this is where whatever you select will be popped up here. So it helps you keep track of essentially where you are in the process. And so I can actually show you one I've done before. So hopefully this works, because I did this earlier and it wasn't working. Yeah. Oh wait. Yeah, okay. It is working, so that's great. That's essentially what we're trying to achieve. Before it was messing up and I thought I had extra work to do, and now I don't, so yippee. We're just going to close that, and let's just do that. Okay, so when you load yours up, you won't have obviously anything here. It will just have this sort of drop down thing with 3 red boxes there, and so that's actually that's the name of your, well, assembly or whatever it is, even a part. And so how you want to create a new simulation, just right click, new simulation. So in the environment box, the box that pops up, you either want to choose kinematics or dynamics. For this, we're going to do dynamics, and I'll just explain the difference. So dynamics deals with mass, so anything which involves simulating against gravity or any of that sort, yeah, you're pretty much going to use dynamics. And kinematics is just seeing how it moves really in space. So for this mechanism, it's either works, but we're going to use dynamics just so I can show you some of the features which come up due to the dynamics option. These 3 options we're going to leave unticked because it's just too complex for the purposes of this video. Maybe in another video in the future I will talk about these, but flexible body dynamics, this is to do with, like, you know, FEA and finite element analysis, all that sort of stuff. And these 2 options are to do with, like, some of the options here, as you can see, like the motor driver. I mean, this is a motor here, so that's kind of to do with that. And we're going to leave these 2 unticked as well. Just give the motion a name. You know what? Let's give this a very innovative name. Oh, tutorial_1. Wow. Okay, so let's just click OK on this. Okay, so now we're just going to orientate this so it's correct. Okay, so for the simulation, I want the red link to be fixed and this yellow one to be rotating in a counterclockwise direction. That's my goal. That's what we hope to achieve, like the previous one in the kinematics one here. So there's only 2 kind of areas we're going to be working in, which is the setup group and the analysis group. Everything else, this will probably be for a future video, as there's just not enough time to talk about this in this video. So I'll just go from left to right quickly. So environment, we've already done this. This is what we chose right at the start, so we're just going to leave that for now. Solution, we're going to come back to this at the end. So obviously you need to solve your simulation, and this is what we need to actually do later on. So I'll leave that for now. Link is the first thing. So this is really important. You actually need to define all of the sort of solid objects within your simulation. That's what this is for. And as you can see here, because we chose dynamics earlier on, it actually has mass properties. Obviously it's 0 here, but you can actually change it yourself because this is automatically defined by an X. So if I just select this, and you can actually just use define, and you can change the values yourself, but most of the time just leave it automatic. It'll be more than enough. You also have other options here, which we won't talk about. You can actually select multiple. So what this will do is NX will see this as a single kind of rigid body. So say if this is part of a larger mechanism, this would move like this, it just move as one whole body. But obviously we don't want that, so I'm just gonna deselect them all. Or deselect down one. If you don't have to deselect, just hold shift and then left click, and then you should be able to deselect. So obviously we've got the red link, fixed link without joint. We're going to leave this unticked for now, but we're going to define it later in the joint box here, which is the next step. A name, give this a name. Let's red link. Wow, amazing name. I'm just going to click OK. Instead of clicking OK, I'm going to click apply, and then I'm just going to click the next one. And I'm just going to middle click from now on. It's just a bit quicker, middle. So that's a way to do it as well. And then click cancel. So now you can see here on the left in the motion navigator we have, okay, I don't name the others, but if you really want to, you can just you can rename them here if you really want to. So there you go. So now we have the links. Now we just need I should mention also, if you go to the links, you won't be able to select anymore. That's it. Like once you have them all defined, you won't be able to select any. So that's a good way to check whether or not you have them all selected, kind of thing. So now I'm going to go into joints. Obviously we have 4 joints, we need to define them relative to one another. So I'll just talk about the joint types. So obviously there's a long list down here. Realistically, the only ones you're ever really going to use is the revolute. I mean, that's for 90% of your simulations. You're going to use this. Anything that spins, rotates, revolves, well, as it's in the name, yeah, anything of that sort, you're going to use that. A slider and cylindrical, this is quite useful. I made a simulation of a V8 engine. I may show it, maybe not, in another video. And I used I think both of these features for that, for the piston head within the cylinder block. So that's quite useful for that. We're going to use, the only other one we're going to be using for this is fixed. So obviously that's to define the fixed red joint, which is what we could have done earlier, but we're going to do it here. So this is a bit more, you can see it a bit clearer. And obviously you have all these other options, which I just won't go into just yet. So action, so this is the action kind of link that you want to perform this joint type on. So obviously let's go to fixed, because we want to define the red one. So the action, if I just click here, what it's done is it's selected the red link, and it's selected the origin as to be the center of the red link in the length direction. Obviously, because this is fixed, this is a fixed link, it doesn't really matter. So this can be anywhere. Like I can even specify it to be, okay, it keeps selecting the vector. Okay, let's just, so I can really put it anywhere. The vector in this case again is not important because it's fixed, so you can really have it anywhere you want. You can even select from this box here, or it doesn't matter at all. Base link will come onto that, so let's just click apply, and obviously you can give it a name as well. And as you'll see here, it gets added to the joints. So there you go, that signifies the fixed. So let's go to revolute, as we need to define now the green one. So we're going to go green, yellow, blue, and I'm going to go in that order for a specific reason. So the green red joint first. So if I just select the green link here, what it's done is it's actually defined the origin to be between the halfway point, but we don't want that obviously, because we want, this is the pivot point here, we need it to rotate around this central point here, otherwise it would be rotating kind of in place here. So the way we would change this, if you just click this drop down box and click this arc ellipse sphere center option, so the black circle with the red dot, not the 4 dots, this one, and just click there on the edge, and now you can see it's actually selected the center. For this mechanism, it's perfectly fine to select the edge as long as you specify the correct vector. It will always work perfectly fine. But say if you want to define it more accurately and you want this dot to be between halfway of the width of the link, you can actually do that. So if you go here and you click the point dialog box on the specify origin option, and instead of existing point you click between 2 points, and now if you do the drop down box with the same option, And so if let me just rotate this like that, and I'll just select the back edge and the front edge, so it's specified 0.2 front edge. Now you can see that kind of green dot, it's halfway between those points. That's one way you can specify a bit more accurately or precisely. So let's click OK. Vector in this case is really quite important, because for a revolute joint, the vector is always normal to the rotation. In most cases, there might be a special case here and there, but most of the time in my experience it's always been normal. And by that I mean the mechanism is going to be rotating in the plane, so we want the vector to be coming out of the plane. So as you can see, there's this y-axis and there's a z-axis, so we want it to be on the x-axis here. And the easiest way to do that is if you just make the mechanism flat to the plane, you just click on, well, you can click on any, and there you go, it's coming out of the page, and that's what we want. Base link, so now we can talk about this. So base link, what this does is, so for this green joint here, it's going to be the red link, because obviously it's the one closest to it. So what this does is this just keeps kind of the relative position between these two. It's not as important for this one because obviously the red link is fixed, but say this one up here, because this whole thing is going to be moving, the green and the blue joint, that's why you need to select the base link, otherwise they'll kind of move separate from each other. That's pretty much it. Limits and settings, we're just going to leave this for now. Name, you obviously can give it a name, and we're just going to apply for this. So now we're going to move on to this joint here. So again, revolute joint, we're going to do this quite quickly now. So you can actually do all three in one, all three options in one. If I just select that edge there, so selected the link, it selected the origin to be the center, and now it's selected the vector to be sort of normal, as you can see right there. So that's perfect, that's what we want. Base link, we're just going to snap to the red one for the same reasons as the green one here, but it's not really necessary in this case, but it's definitely necessary up here. And then click apply, and then kind of let's do the same thing for this. So I'm just going to click the edge there, and base link. So now it's really important, because now once this green link moves, because okay, well this green link will move, right? So we want this blue link to be snapped kind of to that location as it moves, whilst freely rotating. So that's what that is for. And then just click apply, and then we're just going to do one more. We're just going to do right there, and base link, the yellow one. So it's always the joint that it's kind of attached to. We're not going to talk about snap links, as it's slightly more complex for this video. It's kind of used for more complex mechanisms. Maybe in another video I'll talk about this, but for this video I won't be mentioning this any further. We're going to come on to these in a bit. So friction driver, well, not so much friction, but driver definitely. This is to actually drive the mechanism, as you'll see. So let's say we forget to drive the mechanism. It's just, you know, gravity is the only thing that's going to be acting on it, is the only force acting on this. Ignoring the fact that this is floating in midair, but we'll just pretend that we've invented some sort of new physics. But yeah. So let's say, okay, so we've defined it as well as we can. So now we need a solution. So now we have no active solution. So if we go up here now, the solution comes in handy, because we just click that, and solution type will be, in this case, it will be normal run. These three, again, maybe in another video, but it's for this video it's too complex. Flexible body, this is sort of the this is related to this. It's the sort of a flexible link. So this is to do with the flexible body simulations and FEA type stuff. For spreadsheet run, you can actually run this on using a spreadsheet, an Excel spreadsheet, if you really want to. I don't know why, but you can. I don't know why you'd want to, but you definitely can. And articulation, again, this is probably for another video. So we're just going to click normal run. Analysis type, so kinematics, dynamics. Obviously we did dynamics in the beginning. Kinematics falls in the same group. Static equilibrium, this is basically, okay, what would happen if I let gravity do its thing? That's what that option is. So this will just drop pretty much, except for the red one because it's fixed. So we're just going to do dynamics. The time and steps, this is already kind of pre-inputted by NX itself, but you can change this so you can increase the time and steps. I'd recommend increasing the steps and decreasing the steps and see what it does to the simulation. It should speed it up and slow it down. And then we're going to leave these two unticked, especially this one. You can tick this. So what this would do is, what this would do is if you click this and click OK, it would actually solve the simulation. But I'd highly recommend against that. Please learn from my painful experiences, because you'll probably find that if there's something wrong, especially if you're doing quite a complex mechanism, you will probably spend half an hour trying to solve it, and then you'll be stuck there not trying to abort the mission, and then the file won't save, and then you have to do it again, and I'm getting PTSD, I think. But just I'd leave that unticked, please, at my humble request. And you can tick this if you want, and include static analysis, doesn't matter. Specify direction, so gravity. Okay, so in this case it's going up, but you can just easily reverse the direction. It's not really needed in this case because obviously this is we've made our own new branch of physics. I don't know what to call it yet. Maybe leave a suggestion. And I really don't know why they give the option to change the value. I don't know, maybe if you want to simulate something on Mars or the moon, maybe Elon's using this, in his next trip to Mars or whatever he wants to. Okay, let's not go off topic too much. This video is already getting long enough. So gravity, you can specify it. It normally always specifies it, but for this we don't really need it. Solution name, let's give it a name. It's going to be the most amazing simulation, and give it a couple of rows. Fantastic. Solver parameters, we're not going to really look at this because it's too many options, not enough time. That's pretty much all you need, so let's just click OK. And as you can see now, we have the most amazing simulation ever, and its status is now active. And so, but we're not quite finished there just yet. If I click solve right now, so that took about like 2 seconds, but I can pretty much make it instantaneous for this mechanism because it's quite simple. So why you can see that there's loads of these progress status up to whatever, but what we can actually do is, because this is not the correct solver I'm using, so if you right click on your whichever simulation you made and go down to solver, and the one that I use is Recurdyne. Depending on your institution, right now, I'm in Loughborough University. This is where I'm recording this. We use Recurdyne. If you're watching this somewhere else, then you just speak with your maybe your supervisor or your administrator and just double check which one it is. Surprisingly, it's not NX Motion. I don't think that ever worked for me, but it's definitely Recurdyne for me. As you can see, SimCenter Motion is used for it's up here. So once I click Recurdyne, this will actually go away. Ready? Gone. So there's no options to click these now. So there's a few limitations in that sense. But we're just gonna take that as it is. So now if I click solve, pretty much that was instantaneous, and you get some redundant constraints. Don't worry about this. This is not horrific or anything. You pretty much get this in every simulation. I don't know why NX does this. It's quite weird in that sense. You can even if you check it, no error warning found for model check. So that's one way to actually kind of bring peace to your mind, I guess. So now, as you can see, we actually have results. So results are up to date. If we do make a change, each time we need to solve it, because NX only remembers the last time you solved it. So that's really important. Every time we make a change, just click solve. So now it's solved, everything's all good, and we're just gonna click animation and click play. Okay, so as you can see, what's happened is our new branch of physics has just let it drop due to gravity. So that's obviously not what we want. We want it to rotate. So let's just close that. And that's when I was mentioning earlier on about the drivers. So now you want to find the joint which does the driving. So we want this yellow link to rotate clockwise, and so it's obviously going to be joint 3. So joint 3. So now, okay, we're going to ignore this because again, just way too many options, but the options there, so that's nice. The driver, there's 5 options. The one that you most likely will use, and the one that I've pretty much used for all my simulations, is polynomial, as is the simplest really. You can use harmonic. this is useful, say if you have like something like an oscillating fan, anything that oscillates, so you can specify the phase angle to be, you know, 90 degrees, 180 degrees, so it will only rotate that certain amount of time and then go back. So that's good in that sense. These three we just won't talk about now, maybe in another video. It's just way too complex for this video. So polynomial, we're just going to give a velocity. In this case, we're going to do 180. So what this means is, well, hopefully you should know, for each second it's going to rotate 180 degrees, so it's half a rotation, and so in 1 second it's going to rotate twice. You can also give it acceleration and displacement values if you really want to, but velocity is normally more than enough in most cases. So as you can see, it's actually rotating counterclockwise, but we'll leave that for now. And I'll show you how to change that in a second. So let's just click solve. Remember, you have to click solve each time, and then click animation, and there you go. So now it's going in sort of the clockwise direction, but we want it to go counterclockwise. So there's two ways of changing it. The easy way, the hard way. So if you, oh wait, I forgot to mention, any joint which has a driver on it, so you can see with this red arrow here, which kind of like rotates around it, the hinge kind of mechanism here. So easy way, hard way, as I mentioned. Well, actually, now that I think of it, I've kind of got it the other way around. So do as I say, not as I do. I've always done it the kind of quote unquote easy way, but just all you have to do is click that, and it should reverse the direction. And there you go. Now it's kind of going in the counterclockwise direction. Always click solve, and there you go. I can even show you that. I'll show you the way I normally do it. I don't know why I prefer it, but it's pretty much the same step. All you just do is minus. That's it. And so now it should go in the clockwise direction, even though the arrow is pointing the counterclockwise. There you go. So we did like a minus type effect there. So yeah, that's pretty much it for this. We just about hit 22 minutes just now. That's pretty much. I'll probably talk about a few of the other features in an upcoming video where it's a bit more advanced, like how to gather data and sort of using like the 3D contact, as well as like the coupler section here, like to do with gears. That's really quite useful. But yeah, that's all for this video. Hopefully you found it entertaining and informative. Please, you know, like, subscribe. No, I'm joking. A friend told me to do that, so that's why I said that. But yeah, hope you enjoyed, and I'll see you next time. Thanks.